Welcome back, everybody. Couple of quick notes. Oh, London, I like your Egyptian background. That's pretty cool. Quick note, just reminder, Thursday you have exam for chapters 1, 2, and 3. We will finish chapter number 3 today. Then give you a couple of days to catch up, and then it's open from noon to I want to say 10 or 11 p.m. So yeah, 75 minutes. Make sure you give yourself plenty of time. Okay. Now we will be here. I'll be here on Thursday, obviously. Now, one or two things can be set up for Thursday. One, if you have any questions about topics concerning chapters 1 through 3, feel free to bring them in. We can talk about them. If not, I will continue with the next chapter. Okay. And that'll be true for all exam days. Normally, we're face to face. We do the exam in class, and we don't have any lecture. But the advantage of this, of going on with the lectures, it kind of gets us ahead a little bit, and we end up at the end of the semester with 1 or 2 what we call study days. And it's basically an office hour. And 15 minutes, you can come in and ask any questions concerning all the chapters. So, all right, any questions? Well, I shared with you, I sent everyone this file, okay, that was basically talking about the metric units. And we did talk about it a little bit. Now, the key thing about this chapter we're going to be converting units from one unit to another. And the aspect of all this is that every conversion factor we can set up as a ratio. And here I use the example 1 kilogram is equal to 1,000 grams. I can set it up with 1,000 grams in the denominator or set it up with 1,000 grams in the numerator. Now, I know you might want to just take the inverse of that 1,000 and use that number. My suggestion is don't do that. Just leave the numbers whole and just move it where you want it to be. We set that up in that manner because we're going to keep track of the units when we do the mathematics here. And remember here that like units will cancel. Bananas divided by banana equals 1, okay? We talk about algebra, we're using letters, but it's no different than using units, okay? So here you can see where kilogram gets canceled out by the first conversion factor. And so if I were going to stop that calculation with the first unit, I end up with grams as my units. But the problem said I need to get to micrograms. So I need one more factor to convert that 0.125 kilograms to micrograms. And again, I needed to set it up so I can cancel the unit grams by another factor. So my other factor, my last factor here, I set it up with grams in the denominator so you can see how they cancel. Okay. So then finally just basically do the math, and now you have units of micrograms as where you want to get to. Now, every conversion factor is a ratio. Now, we give you these 3 conversion factors that get you from English to metric. 1 inch is equal to 2.54 centimeters. This information is in your shapes table, so it's not necessary to memorize. It's there. But keep in mind that it is a ratio, and being a ratio, I could set it up. Oh, we got one more. There we go. All right, being a ratio, I can set it up in 1 or 2 ways, with inch in the numerator or inch in the denominator, okay? And the same is true for the other conversion factor. 1 pound is equal to 454 grams. 1 quart is equal to 946 milliliters, okay? Now, these conversion factors, normally, you would think, okay, I got a measurement. These conversion factors are not exact, and that is true. 1 pound per 454 grams is a measurement. 1 quart equal to 946 milliliters is a measurement, and therefore is not an exact number, and therefore it could be a factor the 454 and the 946 could be a factor with respect to the final significant digits, okay? So keep that in mind. The other one is, by convention, treated as an exact number, okay? And so check this out. Make note of this. Where is mine? Uh-oh. My pad is not working. This is exact. And these here, not exact values. So they could play a role in your sig figs. Okay, now with that, try to troubleshoot my. There it is. I got it now. Maybe not. Okay, yep, I got it. All right, so the point here is, after telling you which is exact and what's not exact, keep that in mind, because those could be a factor in sig figs, okay? And this one here, not a factor in your sig figs. Okay. And so we have all these ratios that we can set up. It'd be no different than any other ratio. $50 per hour. I can set it up with $50 in numerator or in the denominator. Speed, 100 miles per hour, same thing. Okay. All right. And now the manner that I set them up, for example, if I take these two, depends on the final units that I'm searching for. Okay. And here, if I'm using, I want my final units to be in hours, then obviously I would select this one. If I want my final units to be in miles, and I'm, trying to figure out how many hours, think about it. If I travel 100 hours, okay, how many miles do I get? How many miles do I go if I travel 100 miles per hour? So I set up my conversion factor that I want 100 miles in the numerator and 1 hour in the denominator, because I wanted to cancel. And so there you go. I got 100 times 100. Okay, that's 10 to the 1 times 10 to the 4th, and I'm good to go. And my units are correct. So keep track of your units. Let's go back. So metric units and conversions. We talked about this at length with respect to the units and the symbols. We got M, little, all lowercase, except L for liters, the volume, okay, so uppercase, capitalized, I should say. And then second is uniform, whether it is English or metric, but that's S. So little m, little g, capital L for liter, little s for small. I use this, that table I gave you to kind of give you these conversion factors of going from decimeter to centimeter to milliliter to microliters, okay? So K, it's a prefix, is kilo, it's 1,000 times greater. Okay, so in 1 kilogram, there are 1,000 grams. And 1 kiloliter, there are 1,000 liters, okay? Deci, how many years in a decade? 10, so it's 10 times smaller. And so in 1 meter, there are 10 decimeters. Centi, see, how many years in a century? 100, okay? So it's 100 times smaller. Therefore, in 1 meter, there is 100 centimeters. Milli is how many years in millennium? In millennium, it's 1,000 years. And so it's 1,000 times smaller. And so in 1 meter, there are 1,000 millimeters. Now I'm using meters, but you can just take out the meters and put in liters and grams. Okay. And then micro is that example is the mu symbol, which look at you with a little lip up front. That is 1,000,000 times smaller. So therefore, in 1 meter, there are 1,000,000 micrometers. Okay, so 1 milliliter, 100 centimeters. 1 meter, there are 10 decimeters. 1 kilometer, there's 1,000 meters. And there's 1,000,000 microliters in a meter and 1,000 milliliters in a meter. Okay. All right. So, and there's some little help there for, hint cent. There's 100 cents. I use century, how many years in a century, but there's 100 cents in a dollar, 10 dimes in a dollar. Okay. So on and so forth. All right. So what we utilize is what the book talks about and names it as a factor label method. Okay, it's a fancy name for, hey, keep track of your units and you'll set this up properly. Okay, and there's a couple of steps in which we'll go through. First, identify what units you are looking for. What is your answer? What is the ultimate units at the end? And then identify from the word, the problem is what units you are given, because that's your starting point. And then once you know where you are with units and you have all these conversion factors in hand, you can set up those conversion factors such that you end up with the units that you're looking for, the answer, okay? And so you're multiplying all these units with these conversion factors, which we show as fractions or a ratio. All right, then of course, obviously keep track of your sig figs at the end. Most of the time, the conversion factors are exact numbers and therefore wouldn't be a factor with respect to how many sig figs you have at the end for your answer. Okay. All right. And this last part is this. What you're looking for with respect to units will always be in the numerator. Okay, and what you want to get rid of will be unit-wise, will be in the denominator, because you're going to multiply that by some number unit-wise, and it will cancel out. All right. All right. So, for example, how many liters are in 2,389 milliliters? So we write down what we're given, and the one thing that we don't have, I should have up here, is eventually I want to get in units of liters based on the question, okay? And so that means I'm going to have conversion factors here. And when I set up a conversion factor, guess what? Maybe I can set up a conversion factor, just working the units first, where I want milliliters in the denominator and liters on top. Now, why do I want milliliters in the denominator? Because when I multiply through, my milliliters cancel, leaving me units of liters. Now I can insert the values that I need to insert, the conversion factors, okay? And then just simply do the math. So I got 2,389 divided by 1,000. Now we have 4 sig figs here, 4 sig figs, okay? The conversion factor 1 over 1,000 is an exact number, okay? And so there isn't any, that's not a factor with respect to your conversion. It's not a factor with respect to your significant digits at the end. All right, so here we go. We do the math, and then we end up with 4 sig figs, 2.389. Okay. Now, at the time, you probably would say, hey, I got a milliliters, go to liters. I simply move the decimal point over. And that is correct statement. You can start from here and from the 9 and just move the decimal point over. But if the problem says show your work, then show your work. This is an example of showing your work and how you got that converted. In other words, show the factors. Yes, we understand that you can start right here and just simply move the decimal point over 3 positions and you're at the answer. But do show your work if called for with some converting factor. All right, second one. How many kilometers are in 12,300 centimeters? We write down what we're given. Okay. Note the number of sig figs. We got 1, 2, 3, 3 sig figs to work with. Okay. So I keep track of that because that's how many sig figs I need at the end. And then I write down what I'm looking for, and I'm looking for kilometers, units. Okay. All right. And so I have centimeters. So if I use a factor that I know that in 1 meter, there are 100 centimeters, I can set that conversion factor up first because my centimeters cancel. And then I need another one because I'm not at the kilometer units yet. I need one more factor here, which relates kilometers to meters. Okay, my meters cancel, leaving me with the units of kilometers, which is what I'm searching for. Okay, now if you see this, there's no problem with combining these two conversion factors into one, because notice, you have meters cancel out. So you could have a conversion factor. Every conversion factor I gave you in the metric, I can combine to make one conversion factor, whichever factor I need, because you can see here that if I take 1,000 multiplied by 100, I have the new conversion factor where it is kilometers per centimeter. Okay, but until you're comfortable with that, keep them separate. Okay, keep them separate as far as the conversion factors. So then we end up with 0.123 kilometers. All right, so these are the factors that we gave you in English: 1 cup, 1 pint. Obviously we know 12 inches, 1 foot. If you don't, that's what it is. Okay, from the English unit: 3 feet in a yard, 1760 yards in a mile. One that's not here: 5,280 feet in a mile. And obviously 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. Okay. Every one of these is a ratio, a fraction that you can set up depending how you need it. Okay. Now you can put all that in this picture we showed before where we got the big G. There's 4 Q's for quarts inside the big G. Inside each quart, there are 2 P's for pints, 2 pints for a quart, and then inside each P, we are 2 C's that represent 2 cups. 2 cups per pint, 2 pints per quart, 4 quarts per gallon. Again, all those being conversion factors. All right, so we have this particular question, and they're asking how many gallons is 44.5 cups. All right, so we write down what we're given, and we write down also what we're looking for. Okay, because I don't want, that's my goal there. I want to be in gallons, so I don't want to lose track of where I'm going with respect to units. And so I got cups, and I need to find a way to get rid of cups and get me into another unit. And I know that there are 2 cups in a pint. Okay. And as I set this up, make sure I'm checking my units and make sure everything's correct. Remember, this is a number that I can make it into a fraction by just simply put a divisions in the one underneath. That's the same thing. That's how you make a number into a fraction. Just put a line and the number 1. All right, so at this point, with respect to the calculation, I would be in the units of pint, okay? And so I need one more unit to get me out of pints into something else. Therefore, I know that in 1 quart, there are 2 pints, okay? And I put pints in the denominator. Why? Because pints is what I want to get rid of and get me into another unit that's closer to gallons. I'm not there yet because this conversion factor puts me into units of quarts. Okay. So obviously I need one more conversion factor, and that final conversion factor, you'll see now that there are in 1 gallon, there are 4 quarts. And I set it up with quarts in the denominator. And I finally at the point of gallons. All these conversion factors are exact numbers, so my answer would not be dependent with respect to sig figs on those conversion factors. But I have 3 sig figs, so I do the math. Okay, and I end up with 2.78 gallons. Okay,
I have a question real quick.
sure, go ahead.
So I partially understand why you're doing it this way, but why not just divide that number by 16 to get the same answer?
And that's what I mentioned earlier.
Okay.
Okay. That if you see, you recognize that I can convert these conversion factors into 1, that's fine. Now we're setting it up right now. We're doing simple conversion factors of different units. This same technique. Let me write that down. Good question. And let me write that down on how it's said, because you can see here. Let me clear it up a little bit. Here, a mess. You can see that my pints cancel, quarts cancel, and if I were just to do the math here, okay, I end up with 1 gallon is equal to 16 cups, right? Which I could write also as 16 cups in 1 gallon. So I've combined these 3 conversion factors to give me 1, and that's perfectly okay. Okay. For right now, when we're doing conversions with respect to units English to metric, down the road, we are going to be doing this technique to do conversions for chemical reactions. Okay. And so these conversion factors, in fact, this is a perfect example. A typical conversion factor from a chemical reaction would have at least at the minimum 3 conversion factors. Okay, so this technique that we're utilizing, I'm talking about, is keeping track of your units. We're going to extrapolate that when we get to conversions of chemical reactions and use this process also. Because there you're going to see it's a little bit different, but the thing that they have in common are units. Okay, so yes, for these conversion factors, you can make 1, and that's fine. But be aware how we set that up, because we're going to use that technique when we start doing calculations for chemical reactions. Okay. And I'll give you a quick example of what I'm talking about, so you can see how we can take H2O, break it down to make hydrogen gas plus oxygen. And then we have to balance it. We got 2 here. Okay. Now, if I want to make 16 grams of oxygen, I need to know how many grams of H2O do I need to start off with? A typical equation. And notice I have a relationship of 1 to 2 between oxygen and water, and that's a ratio I'm going to use. Then I have to convert the amount of oxygen into another unit called moles, okay, and then use that ratio between 1 to 2 to get me into water. And once I know that unit of moles of water, I can convert that unit to grams. The result is this, that I put in 3 conversion factors here, okay, to get me eventually to how many grams of water I could make if I need to start off with, if I need to make 16 grams, okay? And all the way along the line, I'm going to keep track of my units and canceling things out, okay? And that's why we're advocating right now to do this longhand and be familiar with it, because we're going to use it down the road. Okay, next one, we got 3.5 yards. We want to convert that to inches. Obviously, we know there's 3 feet in the yard, so here's a conversion factor. The yards cancel, leaving us feet. Then the next one, obviously, we know there's 12 inches in the foot. Feet cancel, okay? And then we do the math, okay? at 3.5. Now the conversion factors keep track of your sig figs. In the top example, we started off with 3 sig figs. We ended up with 3 as the answer. Here, 3.5 is 2 significant digits, okay? The conversion factors are exact, so don't play a factor in determining the ultimate number of sig figs, but our answer has 126. We need to change that to be represented with 2 significant digits. So like we've been doing, we go to the 2 significant digit position, which is the 2. We look at the neighbor, which is 6. Okay, that means that the 2 becomes a 3. And again, do not drop that 6 completely. We convert that to 0. So it'll be 130 inches would be the answer with the correct significant digits, because these are exact. This is not 2 sig figs. (130 inches). All right. I mentioned this before. The conversion factor we give you, that 1 inch is equal to 2.54, is considered to be an exact measurement. It's open up to opinion, but I want to be consistent with all your other sections. But 2.54 centimeters and 1 inch is considered an exact measurement. Therefore, it would not play a role in determining the number of sig figs. The other conversion factors, 1 pound is 454 grams and 1 quart equal to 946 milliliters, are measurements, and therefore could be a factor with respect to significant digits in your answer. Okay, so we take this example. How many pounds are in 248 grams? Well, we know that 1 pound is 454 grams. Okay, we set it up with the grams in the denominator because we want grams to cancel. And our answer is 0.546 pounds with the correct number of sig figs, because those conversion factors, 454 is not exact. It has 3 sig figs, but the 248 has 3 sig figs also. So our answer would end up with 3 significant digits. How many inches in 3.54 times 10 to the negative third kilometers? There's a chance to utilize your scientific notation, keeping track of the toggle switch to make that exponent negative, okay? Or you just move the decimal point over three decimal places, write it longhand. I would suggest trying the scientific notation so you can get the hang of that, because we will be using big numbers down the road. And so we got 354 times 10 to the negative third kilometers, okay? Our first factor, our first factor gets rid of the unit kilometer, okay, leaving us with units of millimeter. Our second conversion factor gets rid of the meter. And finally, our third one gets rid of the centimeter. Yes, as the previous question, I can combine these to make one of them, all right? But I would suggest set it out longhand so you get used to it, okay? Be familiar with the factor label method. Again, I can't overemphasize, we'll be using that technique down the road, okay? Now, also too, I know you've been tempted to set up the ratio, you know, A over B is equal to C over D, and set it up like that. And my recommendation at this time is not to use that technique, okay? You might be good with the first one, but when you get into the second, third, and even possibly fourth, things can get kind of mixed up real quick. So you're better off just using this system here, okay? That way there's no loss of where you're going with respect to the units. Okay. 2-liter bottle contains how many quarts? Well, write down what we know, which is 2 liters, is what we're given, I should say. We know that in 1,000 milliliters, there's a liter. So there's our first conversion factor. Okay. So this takes care of the liters, gets rid of them. And then we have milliliters. So our next conversion factor to get us into quarts is 946 milliliters in 1 quart, and therefore milliliters cancel. You can see here that the units cancel out properly. Now you just simply do the math, plug it in the calculator, 2 times 1,000, divide that by 946, you end up with 2.1 quarts, simply because you have 2 sig figs. Now, if the answer was, if you were given 2.0000 liters as the given factor, then what defines your final sig figs will be the 946, right? Because it's not an exact. So you got 3 sig figs, so your answer should have 3 sig figs. Okay, so keep track, be mindful of that. Sometimes some of the homework problems, they kind of throw that at you, throw a little curve at you just to see if you're paying attention. All right, where are we at? Okay. No. Right. So conversion factors. There's homework, obviously. Practice and practice. With any mathematic function, it's a matter of practice to be comfortable with. Okay. And these factors may come into play somewhere. You never know. I'll give you a real life example. I may mention it before. Let me give you a real life example and let you work it through. Let's say you have 100 milliliters of solution that you're going to inject into a patient. A person needs to do that, and you have to inject that into 20 minutes time. Okay, you have a pump here. It's a pump that will take that liquid and pump it into, the person over here. Now that pump has a rate that is given in units of milliliters per hour. Okay, that is the rate that pump understands. And so given that you have 100 milliliters and you got 20 minutes to put that into the patient, too fast is not good, too slow is not good. What rate would you set that pump at? Okay, that's a little bit of a problem for you to kind of work through, and let you work on it and see what you come up with. All right, but it's a real life situation. I had 3 nurses argue with me about what the rate should be. All right, finally figure it out, but I'm not picking on the nurses. Okay, I'm just saying, kind of be able to use your mathematics skills in the real world situation. Okay, so much for conversion of factors. We're going to talk about a little bit about density, which I mentioned earlier, way back in the beginning, where we talked that density is another ratio, which is mass over volume. Okay, most of the time that ratio is given in grams over milliliters. We did stated that in 1 milliliter is equivalent to 1 cubic centimeter or 1 cc. So there's a conversion factor there for you. Okay. Now, normally, if we have something that's like a solid material that's, maybe rectangular shape, we can easily measure its volume directly, length, width, and height, right? Occasionally, but what if you had something like, I don't know, this pen here? How do you measure its volume? Why would I want to get its volume? Because I want to measure its density for whatever reason. Well, the mass of this pen, not a problem. I just stick it in the math on the balance, I got its mass. But its volume is a little bit different. So we use a technique called volume by displacement. So you can probably figure out that you have a container with X amount of volume, okay? You can measure the starting amount of volume you have in that container. You put your item into that container, and because it has mass and it has volume, the solid, it will displace a amount of liquid. No different than you jumping into the tub and you know that volume goes up, right? If you completely immerse yourself and you're able to measure the tub volume before and the tub volume after, guess what? That difference in measurement gives you your volume. And that's what happens here. We take a diamond, we put it in a cylinder, graduated cylinder. It's one of the tools we use to measure volume, okay? And it has, to begin with, 20 milliliters of water. And we put the diamond in there, and guess what? The volume increased. Makes sense, right? Okay. But the volume now increased to 34.7 milliliters. Now, that is not the volume. That is not the volume of the diamond. That is the volume that it displaced. You have to get the difference between what volume you ended up with minus the volume you started off. So 24.7 minus 20 milliliters gives you the volume that that diamond displaced. Now you have that volume of that diamond. Now you have to take a volume of anything that's not a regular shape and you can't measure directly. And now you simply have to just weigh it. And now you have a density, okay? Okay, so how do we calculate volume? For a box, a rectangular box or a cube, we can simply just measure the sides, right? So we got length, width, and height for a rectangle. And we can take a shoebox and measure it. 24 times 11 centimeters times 16 and measure its volume. And we end up with 4,200 cubic centimeters. Why cubic centimeters? Because centimeters times centimeters equals centimeter square, times centimeters equals centimeters cube, times centimeter equals centimeters to the fourth power, times centimeter to the infinity equals centimeters to the infinity. Okay, you get the gist of it. So that is the volume of that box, direct measure. Now with that information, we're going to start working on density. So density, as we stated before, is simply a ratio. Keep in mind, we can shift that ratio of write in instead of mass over volume, we can write it as volume over mass, okay? The units I mentioned before, normally the standard units are grams over milliliters, but you can see grams over cc or grams over cubic centimeters, okay? And think of density as how much matter in a given space, okay? So obviously we know that the most dense state of matter is the solid, whereas the least dense is the gas. And that's because the volume involved here, the molecules are so far apart from each other for gases as compared to solids where they're much closer together, okay? And so we can, here's an example of gold has a density of 18.9 grams per cubic centimeter, pretty heavy. What we do is a tool, we look at water, pure water at 25 degrees has a density of 1, okay, 1 gram per milliliter. And anything that's greater than 1, if it's not soluble in water, will, if in the presence of water, will drop like a rock. So obviously gold has a density much greater than 1. And so in the container, gold would just drop to the bottom of the container. And anything with the density less than 1, it will float. So that's why, again, why ice floats, because the volume of a set amount of water expanded and that ratio got less than 1 and therefore it floats. Now, ways to calculate density. We simply calculate the density by itself, simply dividing the mass over volume. Okay, that's one type. The second type is calculating the mass or volume given the density. So if I know the density of let's say, for example, water, we say water has a density of 1 gram per mil. Think about that, 1 gram per 1 milliliter. So if I have 1,000 milliliters, guess what? I have 1,000 grams, right? If I have a thousand grams, guess what his volume is? 1,000 milliliters, right? Because of that ratio, which is equal to 1. But to help you out the system, we know that water, and we're going to use water here as an example, is 1 gram per cubic milliliter, okay? And I can set it up as 1 milliliter per 1 gram, either way, okay? And so our question is, how many grams in 150 milliliters of water? Okay, so I'm looking for grams. So grams needs to be in the numerator, right? Because my milliliter is going to cancel. So I write down my 150 milliliters and I use a conversion factor on the left for 1 gram over 1 milliliter. Check my units. Milliliters cancel, and guess what? 150 grams for 150 milliliters. Okay. Okay. It's no different than this ratio. Let's say you're making $50 per hour. Okay. If you work 0.5 hours, how much money is that? Now, obviously, you can work it real quick in your head because you equate $50 per hour and you got it set, right? It's in your head. Obviously, wouldn't that be $25? Okay, well, let me set it up using this factor method. I got 0.5 hours. Okay, there's my conversion factor. I want dollars on top, right? Per 1 hour, because I want hours to cancel. So obviously this becomes $25. All right. All right, that's that factor label system, keeping track of your units. All right, so here's the density of chloroform. Chloroform is just a chemical, used to be used to knock people out when you had an operation. They don't use that anymore. But it has a density of 1.48 grams per milliliter, or I can write it as 1 milliliter per 1.48 grams. Which one I use depends on the question. So what is the density, for example? We keep that in mind. So we're going to run through some different kind of calculations. Here's a straightforward calculation of a density. They're giving you that the density of this necklace is 484.56 grams. And it had a volume of 25.64 milliliters, okay? Well, you set that up, right? Mass over volume. And, you know, you look at the number and you say, does that number make sense? 18.9. Here we go, starting to analyze the answer. Does that answer make sense given the mathematics that you did? And you think about it. I got the denominator is much smaller than the numerator. So yes, that answer makes sense. Okay, because if I would have let me type this out in 0.90. If I would have done the mathematics and I got an answer that looked like this, then you need to ask yourself, did that number make sense? If I get an answer like that, 0.0529, you know, forget all the other numbers, but let's go ahead and truncate it. 4 sig figs right there, because that's where we're at. And let's say you got that answer and that's what you're gonna write. Think about that answer. Ask yourself, does that answer make sense given what I'm doing to the mathematics? What I simply did was just inverse that ratio, 25.64 and divided by 484.56. Obviously, I wouldn't blindly write that number. You know, first look at that number and make sure that it makes sense given the mathematics that I'm doing. And here the numerator is much bigger than the denominator, so I should get a number much greater than 1. Okay, so I wouldn't get a number 0.0529. I wouldn't report that simply because of the mathematics being done. All right, so that is the density. Notice the units then go away. It's grams per milliliter. They don't cancel each other out. Then units are not alike. They're dissimilar units. They don't cancel out. They go along. Okay, now if the density, let's go back to an example now where you're given the density of 1.48 for this liquid called chloroform. They're asking you how many grams would 17.54 milliliters of chloroform mass. In other words, how much does it weigh if I were to measure out? So I write down, whoa, that's a big pen, got the wrong pen. If I were to weigh out 17.5 milliliters, okay, I need to set up my conversion factor. So I got G up front, milliliters in the bottom. And so it's 1.48, excuse the big pen. Don't know why I got so big there. And divide that by 1 milliliter, okay? Now, setting that up, my milliliters cancel out. Bam, I got that problem set up properly. Okay. So then just simply do the math, plug it in there. That's what I'm given. That's my conversion factor. Notice how milliliters cancel. Therefore, if I were to measure out 17.5 milliliters of this chloroform liquid, it should have a mass of 25.9 grams, given its density of 1.48 grams per milliliter. All right, now here's this similar scenario, but now we're going the other direction. They're giving you 0.0735 grams of chloroform. You need to measure the volume. Okay, so we write down what we're given using the same conversion factor, the density of chloroform, except we're going to invert it because we want milliliters in the numerator and grams in the denominator. You can see the grams cancel. And we have 3 sig figs in both cases. Now, density is a measurement. So keep this in mind. It's not a conversion factor. It's used as a conversion factor, but it's a measurement in both cases. Therefore, could be a factor in sig figs. It's not exact. It's a measurement. Okay. So you can see 1.48 has 3 sig figs, and 0.0735 had 3 sig figs. So therefore, our answer should have 3 sig figs. The same is true for the top example. All right, so that's some examples of utilizing chloroform, density calculations, okay? All right, which brings us to kind of energy. And this is stuff you already know. Really, if you think about it, it's common sense. You know that hot molecules move fast, okay? Put your hand over some boiling water. Tell me those molecules are moving pretty fast and they're burning your hand, okay? And why? Because they have a lot of high energy. And the converse is true. Because they have a lot of high energy, they can be, if you remove the energy, then they're going to slow down, okay? So they move slow, and guess what? Their energy drops, okay? Their energy level drops. Now, temperature is simply a measurement of the result of putting energy into a system, okay? Temperature is not energy. It's a measurement that results due to the amount of energy put into a system. Now, we have 3 scales. Obviously, we have the Fahrenheit scale. And then we have the Celsius, which is a metric. The Fahrenheit is the English units. Celsius is the metric units. And we have a third one, which we call Kelvin. Kelvin has a temperature scale that he is Lord Kelvin. He's a British scientist. The thing about these 3 conversion temperature scales is that the Fahrenheit goes to infinity, as does the centigrade, okay? in both directions to infinity with respect to the value. Kelvin, on the other hand, stops at 0. This is what we call absolute 0. And that is where all matter theoretically stops completely. Okay? We haven't attained that level yet. We've come close to it, but not close enough. And there's some very interesting type of physical properties of matter occurring down at that low temperature. A lot of work being going on. So anyway, you got three temperature cases. Now, Celsius and Kelvin are related to each other in the means. In other words, if I have Celsius and I need to go to Kelvin, I simply add 273 to my Celsius temperature. Okay. And that information, again, is given to you in the shapes table. So it's not necessary to get it memorized because you have the shapes table there. Okay. And so, but to convert from one unit to the other with respect to Celsius and Fahrenheit, those are the conversion factors. If you have the temperature Fahrenheit, you want to go to Celsius, subtract 32 and then divide by 1.8, that gives you Celsius. And if you have Celsius, we'll go to Fahrenheit, then take Celsius temperature, multiply by 1.8, and then add 32 to that. With respect to Kelvin, you have to go through Celsius and just simply add 273 to whatever the Celsius temperature is. If your problem is giving you a temperature in Fahrenheit and asking you to convert that to Kelvin, then you got to convert the Fahrenheit to Celsius first and then add the 273. Okay. And so that's the example here. Temperature can get up to 115. Try it yourself. So you could come up with 46 Celsius and 319 Kelvin. Okay. But these factors, conversion factors, again, are given to you in the shapes table. So measures heat. We're really talking about energy here. Okay, of the two beakers here, which has a higher temperature? Well, that's kind of a crazy question because if you look at A and B, they both have a thermometer in there and they're both at 100 degrees Fahrenheit. So obviously they both have the same temperature, more than likely because of the same liquid, okay? But the question is, which has the greater amount of heat, A or B, or the greater amount of energy? Okay. Let me put it to you this way: if you had a choice to have that warm water spilled on you, which one would you select, A or B? I know neither, but if you had a choice, or let me put it this way: if you had a choice of having boiling water spilled on you, would you rather have a big pot of water that you're boiling, trying to get ready to make some spaghetti, or a little tiny small coffee, maybe you're gonna make some tea or something? Which would be, obviously you don't want neither of those to be on you, but if you had a choice, which one would you have? The big pot of water or the little teacup of water heating up to boiling? They're both boiling the same temperature. Which would you pick? I would pick B here, excuse me, and I would pick the smaller pot because even though they're both heating at the same temperature, there's less mass in the smaller cup. Okay, so there's less energy. Yes, it would burn me, but it wouldn't have that big an effect, a smaller amount of material. Okay, and that's why, if you think about it, it would take a period of time to start boiling a big pot of water to boil spaghetti compared to a little small pot to boil a little bit of water to make a cup of tea, because there's more matter in the big pot. It takes more energy to get that pot to boil, and therefore has a lot of energy and destructive power compared to the little cup. So if you ever hear about out in the weather, you're talking about El Nino and La Nina, we're not talking about little kid, little boy, little girl out there in the Pacific. It is a body of water that a very large body of water, and it has a little bit slightly different temperature than the rest of the ocean, but there's so much energy there because the body's so large that it has a great effect on the world environment. Okay. And the only difference between La Nina and El Nino is the quantity of water they're talking about. Smaller quantities, La Nina, larger quantity, El Nino, which affects, like I said, our temperature around the world. So a thing about nature, when we talk about heat transfer, remember, nature always goes from a high temperature state to a low, okay? So heat transfers from high temperature to low. And it's not the other way around. It's not like you're gaining coldness, okay? Some people say that. We're talking about the transfer of heat. And that has nothing to do with coldness. As you remove energy, it gets cold. You put in energy, it gets warm, simply put. Okay, so consider you're holding a cooking straight out of the oven. What is losing heat is the cooking, and what is gaining heat is your hand. Okay, because coming out of the oven, the cookie is a higher temperature state, higher energy state than your hand. So it's going to be a transfer of energy through your hand, and transfer pretty good because it's pretty hot and it'll burn you. Okay, so nature goes from high to low. All right, so if we had a piece of a metal placed in the freezer and then the metal is put into a bucket of hot water, does the temperature of the metal increase, decrease, or stay the same? What do you guys think? Okay, you got a metal spoon, metal piece of metal, could be a spoon or something that's in the freezer. And then you take it and you put it into a pot of hot water. Does the temperature of the metal increase, decrease, or stay the same? What do you think? Where's the energy go? From high to low, right? Who's got the high energy? Or the bucket of hot water? Who's got the low energy? The metal. So heat goes from the hot water to the cold metal. Eventually, that temperature is going to equate. So the metal temperature goes up. That means that the hot water temperature goes down. And eventually, you know this, right? If you're making yourself a cup of coffee and you inadvertently leave it there, come back in about half an hour, what has happened to that cup of coffee? It cools down. In fact, if you leave it alone long enough, it's going to go to room temperature, right? Because all that energy it had is displacing it into the environment. All right, so temperature of the metal increases as it gains heat, and temperature of the water decreases as it loses heat. All right, so don't forget the chapters, okay? Don't forget the worksheets. You got YouTube videos with respect to Dr. Kim's YouTube videos, and you got this one here that I record and upload it here later. I'll upload it here in a bit once it gets converted. Don't forget the chapter problems, practice the conversions, okay? And don't forget sig figs, significant figures. That's not going to go away. Sig figs will be there until the end of the semester. And this is the beginning of week 3. That's pretty quick. So we got about, what we got, 13 weeks or so left. All right. So with that being said, that, ladies and gentlemen, ends. I forgot to turn my video back on. Sorry about that. We're going to have a recording and no video. All right. But you still get a recording. No problem. All right. Any questions, comments, concerns? Okay. Good luck on that exam on Thursday. Don't get too freaked out. Just go in there prepared, you shouldn't have a problem. Look at the homework. Homework questions are very similar. Okay. And like I said, if you have 75 minutes, please don't wait until like, 30 minutes before it shuts down to go in there and try to do it. All right. Give yourself plenty of time and to do the exam. And I will be here. If you have questions, you haven't done it yet, come on in, bring the questions. We can go over it. If not, we'll jump on to chapter 4. All right. All right. Hey, we got, yeah, there is a Zoom. Yeah. For every exam, there'll always be a Zoom. Okay. And like I stated, we'll be going over either questions you may have concerning the chapters for that exam, or we'll move on forward to the next chapter. Okay. Well, we finished a little early, so yeah, I don't have a problem with, stopping in here. Unless you guys have any questions, we can go over the questions. If not, I'm gonna go ahead and shut her down. No questions?